So Mr. Bergman, we're back again, and the very first video that we talked about this equation to unite everything together.
So when we talk about gas laws, it's called the combined gas law, and it is, so P1 V1 over N1 T1 equals P2 V2 over N2 T2. Say that 5 times fast. And what you've got is the initial conditions of pressure, volume, moles, and temperature, and equals
the big four we talked about.
Final things, right? So we also talked about the fact that oftentimes some things are canceled out, and what we most often cancel out is we have the same amount of moles of the gas, and those are the ends. So if we were to cancel off the ends, then if they're the same number, they would cancel, and then we can have PV over T equals PV over T. And really, folks, this is a simple problems where you're just going to be doing some kind of math stuff. So let's say, I got a problem. So here's the problem, Mr. Demetrius. So let's say that I have a balloon. So make a balloon, maybe. Balloon, there's a balloon, and the balloon has a volume of 13 liters. And let's say it's here in Houston today. And so we'd say the temperature today, it's a very comfortable day. Let's say it's 20 degrees Celsius, I'd say, something like that. And it's at sea level, so let's say it's at 760 millimeters of mercury. Now we're going to take this balloon and we're going to go back to Mr. Bergman's home that he used to own in Colorado, and we'd go up to a high altitude where it is colder. So the new temperature there might be, let's say, 5 degrees Celsius, because it's a much cooler day. That'd be like about maybe 40 degrees. But the pressure, big change in pressure, the pressure would be, let's say, 605 millimeters of mercury. So the question is, what happened to the balloon? What's the new volume of the balloon? So, folks, this is a problem where we just have to plug in our numbers. However, there's one critical thing you have to do. What do we have to do, Mr. Dimitrievich?
Well, there's two things here. One is you have to take care of temperature. You can never do any problem in any gas law problem in Celsius. It has to be in Kelvin.
So we have to convert the Kelvin. So we're just going to add 273 to both those numbers. We'll just go ahead and round that. So that'd be I'll do that with a calculator. That'd be 278 Kelvin, and that one would be what? 298, 93, I think.
Thinking 25 degrees is room temperature, sorry. Right.
Yeah. So we got 293, so we're just gonna plug them in. So we're gonna plug in our P's. By the way, the P's and the V's just have to have the same units. It doesn't matter what the units are as long as they're consistent.
And just as a reminder, I put before and after here. The ones are the initial values. So all the values over here, this is our one category.
Yeah.
And all the values over here are our two value. And I like to do this, and Mr. Bergman and I, we may do this a little different. I know that law students like to do this, is just plug in and see where the number's left over. I like to rearrange in advance. Either way works, but in this case here, I like to say, well, and we're doing this, I'm gonna write T2s for these, and I'm gonna write V1s for these, because this is our before, and this is our after. What that means then is we're trying to solve for this, or we're trying to solve for this variable. Right. Now, if you want to, I like to isolate the variable by itself before I plug numbers in. I'm guessing that you're a plug and chug man, which is put everything in and solve for a variable.
I think it's easier that way.
So if we do it this way, we're gonna take all the numbers, and again, these numbers right here, it's incredibly important that you do not mix and match the T's and the ones and the twos. So if our P1
is 760 times 13, so put parentheses, 13 liters over 760, temperature.
Temperature one, which is
293, equals P2, which is 605, times V2, that is going to just be V2 because we don't know what it is, and T2 equals 278. Now let me give you a shortcut, guys, that I think will make your life crazy easy. So you know that when you've got a big set of numbers and you got a variable, that there's this thing called cross multiplication. Here's the deal. The one that contains the variable, all right, the cross that contains the variable, which is this cross right here, you divide. The ones that does not contain the variable, you times. So on my calculator, what you're going to do is this times this times this, divided by this, gives me V2. So it's multiply with the ones with no variable, divide with the ones with the variable. You always start with the multiplication one first. So as you can see on the calculator, I've got 760 times 13 times 278 divided by 293 divided by 605, and I come up with 15.5. So the volume is 15.5 liters of, so let's think of this. Does that make sense? The volume started at 13 and it went up to 15. Does that make sense? Now, you can think this through. The temperature dropped, which would shrink the balloon, right? Because the molecules are moving slower. But the pressure went down, which expanded the balloon.
And this is one of the things we talked about. You can't ever just compare. If you only want to see what one thing is doing, you have to hold everything else constant. In this case, we let everything run wild, and it was okay because we had them all corralled into this one equation. Normally, if I just said to you, hey, the volume is this, if the temperature goes up and the pressure, we'd have a lot of difficulty when there's more than one moving part. This equation ties this all in, so we couldn't make the assumption of, oh yeah, the temperature goes up, therefore the pressure goes up, or therefore we'd have to do it a different way.
All right.
So in this particular problem, you see we have a balloon and we're messing with the balloon. And as a reminder, anytime that you change variables, we use this equation. The problem, it tells us the pressure of the original balloon is 1.30 atm. And I'm going to write P1 here because that's the original pressure. Mm-hmm. The volume of our original balloon is a paltry 2.00 liters.
It's a 2-liter balloon. I see that, yeah.
2-liter balloon.
And now we're going to change the conditions.
Now we're changing the condition. If you take a look at the problem here, it says that the new volume, we'll call that V2, is now 4.36 liters.
Got it. So the question, of course, is what is the new pressure? Now, that's weird. Wait a second. In our equation, we've got these T's, Mr. Dimitrowicz.
And we haven't even referenced them. Now, typically in a problem, if we don't include a variable, we're just saying that it's constant. Yeah. If we'd have written this a little more clearly, we'd have said, hey, temperature is constant. But in this case right here, since the temperature is not included in our equation, we can get rid of the temperature.
And as a note, guys, this is actually a special law. P1 V1 equals P2 V2 is actually called Boyle's law. So when we cancel out the temperature, that's called Boyle's law. Not that important that you know that, but anyways, that's what the deal is.
And also, I was really gentle in this problem here with 2 liters and 4 liters. You realize they could have given us milliliters here and liters here, and we'd have had to convert to the same unit.
And so the key is it has to be in the same unit.
Yeah, as long as it's in the same unit, we're okay.
So we can just plug our numbers in, right?
Yeah, so our P1 right here, wouldn't it be 1.30 atm? And our V1 is 2.00 liters.
2.00, yeah.
And it's going to be equal to, and in this case here, we know what our V2 is, but we don't know what our P2 is. So we're going to go P2.
P2 is our X, if you will, right?
Yep. And our V2 is 4.36 liters.
And so I'm just going to take 1.3 times 2, right? Because this equals 4.36x, or P2. Then I take whatever that comes out to, which is 2.6. I then divide that by 4.36. And I get 0.596330275,229.
So I got so carried away by the beauty of the rest of them.
9633027. Come on, write them all out. 33027.5. Wait. What did I do wrong?
Well, a couple things. One, you ignore significant figures.
Yeah. Because folks, we only have 3 digits. So you can round this to where? 3 digits, 0.596, right?
The other thing is this, and I want to get us to get in the habit of canceling units and whatnot. We have liters over here and liters over here. They cancel, and that leaves us with the only unit that we need in this problem, which is ATM. So our final answer is ATM. Now, we could do a bunch more problems, and we are going to do it in class, but there's 2 things I want you to take away. Number 1, and Mr. Bergman mentioned this at the beginning, the units of any particular variable have to be the same. So if I give you liters here and nanoliters here, that's no good because you have to convert them to the same thing. Similarly, if I gave you another problem and I gave you pressure in atmospheres and pressure in torr, you've got to convert them to each other.
Yeah, and the only one, of course, the temperature, that's not in this problem, but temperature is always has to be in Kelvin.
And then the second thing is simply this. Make sure when you've written your equation out that you cancel whatever variables you don't have. Again, we're going to practice a ton of these, aren't we?
Yep. We'll see you in class.
See you next time.